Hi, my name is Mariano Scazzariello and I will present the paper Sibyl, a framework for evaluating the implementation of routing protocols in FRRouting. This is a joint work with Tommaso Caiazzi, Leonardo Alberro, Lorenzo Ariemma, Alberto Castro, Eduardo Grampin and Giuseppe di Battista. Nowadays, data centers have become a fundamental part of the internet infrastructure, since most of the main online services are hosted inside them. Verified data centers functioning is crucial to ensure business continuity. Data center networks are complex, since they are mostly built using high-density architectures with a high level of redundancy that guarantee constant bisection of the available bandwidth. This intrinsic complexity is exacerbated by the presence of heterogeneous network equipment, which has different hardware specifications and software implementations that, being very complex, are likely to be bug-prone. In fact, Microsoft states that 36% of failures in their data centers is caused by software bugs, while another 27% is caused by configuration errors. All these aspects make assessment of routing protocols and configurations in data centers very complex. Moreover, the lack of standard procedures and testing methodologies justifies the development of solutions for such a critical task. The first contribution of this work is to fill this gap, proposing a methodology for testing routing protocols in FRRouting topologies. We focus on FRRouting, since they are the most widespread topology in hyperscale data centers. A vast literature focuses on model-based verification. However, these works can consider the impact of software bugs, since they perform static configuration analysis and assume correct and bug-free implementations. On the side of emulation-based testing, CrystalNet from Microsoft stands out. This work highlights the need for a system to test large-scale data center networks. However, a methodology isn't proposed, and the system is not open source. For those not familiar with FRRouting, they are a special type of closed network. They provide high redundancy and constant bisection of the link bandwidth. In addition, they do not require specific and expensive hardware, but they can be built using commodity switches. To describe a FRRouting, we adopt the terminology used in the RIFT protocol draft. A typical FRRouting is composed of 3 or more levels of switches. A 3-level design is composed of an aggregation layer that links together different points of delivery, in short pods, made of 2 levels of switches. A pod is a set of leaves that are directly connected to the server farm, plus a set of spines, fully interconnected to the leaves. Each switch has key ports pointing north and key ports pointing south. The aggregation layer is composed by top-of-fabric switches, in short TOF, that provide inter-pod communication. A TOF is connected to at least one spine per pod. The number of links between a TOF and the top spines of a pod is called redundancy factor, denoted with R. Varying this parameter leads to a trade-off between redundancy and the number of supported servers. This divides FRRouting topologies in 2 categories, single-plane and multi-plane. Speaking about our methodology, it is based on the following milestones. FRRouting have regular characteristics. This allows to focus on specific topology elements to obtain results with a general value. Performing tests that measure actual times can be misleading, since timings heavily depend on the used hardware. Also, assuming that the system clocks of nodes are perfectly synchronized is not realistic. Hence, we evaluate the implementations being oblivious as much as possible concerning the actual timings. Finally, routing protocols can be conceptually very different. For this reason, we adopt a black box method, disregarding as much as possible the internals of the implementations. The methodology, leveraging on the structural properties of FRRouting, defines 2 main test categories: failure and recovery. Failure tests induce many types of common faults in data centers and measure how implementations react to those faults, while recovery tests measure how implementations react when the network is restored. To cover all the failure and recovery cases, we define a failure and recovery test for each type of node, in particular a leaf, a spine, and a top of fabric, and for each type of link, that is leaf spine and spine TOF. Moreover, we define a partitioned fabric scenario, which is the most disruptive failure, since a TOF node is completely severed from access prefixes of an entire pod by multiple spine-TOF link failures. Each failure test follows these basic steps. Start up of the fabric with the initial protocol convergence, perform the failure, capture all the PDUs until reconvergence, and stop the network. Instead, each recovery test performs the following. Start up of the fabric with the initial protocol convergence, perform the failure, wait for reconvergence, recover the failed element, capture all the PDUs until reconvergence, and stop the network. For each test, we consider 4 main aspects. The first one is the protocol convergence. This aspect aims to check that, after an event, the node's data plane forwarding tables reach the expected state. If the check fails after a maximum number of attempts, the test is aborted. The second aspect is the messaging load. The purpose is to determine if the protocol overhead grows smoothly with respect to the topology parameters, which are the values of K and R, the number of nodes, and of interfaces. Namely, we measure the number of packets originated by an event and compute their aggregate size. To evaluate the ability of an implementation to limit the blast radius of a failure or a recovery event, the methodology defines a locality metric that is computed with the following algorithm. First, for each link of the network, the number of packets received by the interfaces of that link is computed. Second, a topological distance is associated with each link of the network, computed as the distance from the event. Third, the total number of packets received from all the interfaces having a certain topological distance is computed. The result is a vector where each element is the number of packets captured at a specified distance. We summarize it into a scalar value, giving a larger weight to packets that are far from the event. The way locality is considered allows to perceive the blast radius of an event, but it doesn't give any information about the number of rounds when this happens. Packets could be received all at the same time or in different timings. However, considering this aspect being oblivious as much as possible with respect to the actual timing is a challenging task. To do that, the methodology introduces a novel representation that describes how the states of nodes are synchronized by routing protocol packets. We call it node state graph. Here we have a K2, R2, FAT3, and the node state graph relative to an event on this topology. A node in the graph represents a switch of the network in a certain state. An edge represents a set of packets from the upper node that contributes changing the state of the lower node. In particular, this node state graph is the one generated by a leaf node failure on a BGP implementation. To compute the node state graph from the outside, we use another representation called the node state timeline. This is built ordering all the PDUs captured during an event. For each node, packets are partitioned into sets of consecutive received and sent packets, called receiving groups and sending groups. Then, packets belonging to the sending groups are linked to the relative ones belonging to the receiving groups of other nodes. For each node, we associate a state based on the groups. If the first group of a node is a sending group, we associate a state S1. For each pair of receiving and sending groups, we associate a state Sj. If the last group is a receiving group, we associate a state SH. As an example, TOF122 has two states, S1 associated with the first two groups, and S2 associated just with the last group. From here, we build the node state graph, creating a node for each state, and an edge for each set of links from the sending group of a node to the receiving group of another. This graph allows us to perceive the number of state changes that the network traverses before the convergence, that we call rounds. Using the graph, for each vertex we can compute its state round value as the length of the longest path from a source to that vertex, needed for reaching the convergent state. Also, we can compute the maximum value among the state round values of the vertices, called state round value of the graph. In this example, it is easy to notice that the state round value of the graph is 4. Assessing the methodology in a physical data center would be unfeasible due to the overall costs, and since it limits the automation and reproducibility of the experiments. For these reasons, we leverage on a virtual emulation environment that gives the flexibility to freely scale the topology size and to automate the testing stage. Moreover, emulation allows to test real software implementations, and this is not achievable using simulators, which consider correct and bug-free implementations. So, our second contribution is Sibyl, a software framework that implements the methodology. Sibyl architecture assembles existing tools, with new ones specifically devised for the purpose. We use Katara as the network emulation system that can run in a Kubernetes cluster thanks to the Megalos extension. In this way, we can faithfully emulate large networks. To automatically generate and configure FRR topology in a Katara suitable format, we use the VFTGen tool. We evaluate the methodology and Sibyl in 3 use cases. Such use cases witness a wide spectrum of situations where Sibyl is effective for analyzing, comparing, developing, and debugging routing protocol implementations. In all use cases, we performed all the tests proposed in the methodology. In this presentation, we will focus the attention on the leaf node failure test, that is taken as an example. However, all the results are publicly available at the link shown in the slide. We use 2 execution environments, one on a local cluster composed of 22 virtual machines, while another on the Azure cloud composed of 160 VMs to scale up to 1,280 nodes. Note that all the figures shown from now on are automatically generated by Sibyl. In the first use case, we analyze BGP, since it is the de facto standard for cloud-based data centers. We use the FRRouting BGP implementation. We performed all the tests of the methodology on the topologies identified in the figure. Here, the x-axis represents the redundancy factor, while the y-axis represents the value of k. The color intensity of the blue heatmap in the background is proportional to the number of nodes in a topology with the corresponding values of k and r. The 3 numbers represent the number of switches, interfaces, and supported racks in each topology. Boxes with the red border are the topologies deployed on the Azure cluster. The results of the messaging load confirm that the implementation has good scalability, since it doesn't manifest any performance degradation varying k and r. Moreover, we found that the number of packets exchanged by nodes isn't affected by the number of nodes in the network, but it only depends on the number of interfaces of each node. In fact, as shown in the figure on the right, on a k equals 4 and r equals 4 topology, exactly 2 packets are exchanged on every link, and we found analogous results for all the other topologies. This figure is also useful to reason about the locality. In fact, it is evident that the BGP implementation, in case of failures, floats all the nodes in the network. This leads to 2 main considerations. First, BGP doesn't contain an event locally, but spreads the information to the entire fabric. Second, the number of packets traversing a link is constant. From the rounds point of view, the implementation shows a very stable behavior, with 4 as maximum number of rounds in all the experiments. We obtained analogous results in all the other types of tests, confirming the stability of the FRR BGP implementation. This use case highlights and confirms that all the devised metrics give a different point of view that can be exploited for evaluating implementations. Moreover, experiments on larger topologies prove that Sibyl can be useful for testing in virtual massive scale data centers. In the second use case, we show how Sibyl can be used to support the implementation of new features and to evaluate prototypes. Here, we focus on RIFT Python, the only open source available implementation of RIFT, routing in FAT3s, that is a FAT3 specific routing protocol under development at IETF. RIFT is a hybrid link state distance vector protocol that aims at minimizing configuration and operational complexity. It includes some novel mechanisms, such as the negative disaggregation, which allows the automatic prefix disaggregation in case of failures. During our analysis, we found some critical scalability issues, which are expected since the Python implementation aims only to ensure the correctness of the draft. Moreover, RIFT Python was missing the negative disaggregation feature, so we decided to implement it using Sibyl and the methodology to build an integration pipeline to test all the code changes. We also verified the interactions between nodes using the node state timelines and the expected properties of the node state graph to confirm that changes didn't cause bugs. As a byproduct, we analyzed how RIFT Python performs against FRR BGP on the topologies where the implementation converges. The comparison is fair since our metrics don't consider temporal tied aspects. We have that RIFT Python exhibits good results, even if it's a prototypical implementation, and shows the protocol potential. As mentioned before, as the topology scales up, the implementation presents performance issues. This causes a significant jump between the values obtained for a K2-R2 topology and a K6-R6 topology. This is particularly evident for the max round values that theoretically must be the same, but practically range from 3.4 to 13.8. In this use case, we showed that Sibyl is a valid support during the development, and that the methodology can be also exploited to evaluate prototypical implementations. In the third use case, we analyzed the Juniper implementation of RIFT, searching for inefficiencies that are not captured by unit tests. This shows the usefulness of Sibyl and of the methodology also for production-grade implementations. Usually, when an inefficiency or a bug is detected, the root cause analysis is done by examining logs, either manually or automatically. In large fat trees, this could result in an error-prone task, since information coming from all the nodes should be integrated to get a global view of the network interactions. Instead, the node state graph already provides this global view. As an example, we spotted a communication inefficiency analyzing the leaf node failure scenario. On the left figure, we show a node state graph which presents the inefficiency. It is easy to notice that the red packet is bounced back between nodes that have already received it. We reported this inefficiency to the vendor that fixed it, and on the right you can see the node state graph of the same experiment after the fix. This last use case shows that Sibyl and the methodology are also useful for debugging vendor implementations of routing protocols, without having at disposal their source code. In conclusion, this work addresses the lack of standard methodologies and tools for testing implementations for routing protocols in data centers. We target fat trees that are the most common topologies, developing a methodology that doesn't depend on the workload time, the execution environment, or the implementation internals. The second contribution is Sibyl, a framework that provides a flexible testing environment for protocol implementations, leveraging on network emulation, that allows to run real and bug-prone software. We performed an extensive evaluation that proves the efficiency of the methodology and of the devised metrics for analyzing protocol implementations. In particular, we found that the node state graph representation is a valuable support tool for understanding protocol behaviors without entering their internals. We highlighted the usability of Sibyl for implementing protocol features, proving its effectiveness in the analysis, development, and debugging, also for production-grade implementations. Moreover, our evaluation highlighted that the FRR BGP implementation has a very stable behavior and also a good scalability, and that RIFT is a very promising protocol. As next steps, the methodology and Sibyl should consider tests involving multiple node and link failures. Moreover, it should be possible to support different topologies and routing solutions, even non-distributed ones. Another important improvement is the development of a mechanism to automatically verify structural properties of the node state graphs. Thank you for watching.